Hello everybody. We're still talking about the absorption, and we will see in this video an example of absorption of ammonia from air using water as a solvent. This example has been solved in a previous video that I posted before in the Microsoft Excel series, and we saw in this example that we used ammonia with or the ammonia mole fraction in air was 10%, and we used pure water as the fresh solvent. And our goal was to achieve 95% removal of ammonia from air. So this air would contain 5% of the ammonia that entered with the feed gas. We did all the calculations and we saw that we need 6 theoretical stages or ideal stages, and we used almost 1000 kilomoles per hour of water. And we're gonna solve this example in Aspen Plus, but one thing here was that we had the equilibrium data in Microsoft Excel as like fixed numbers, so we didn't have the flexibility to change anything in the system that will affect the equilibrium data. But we have this option here. We can change the operating parameters so that we can change the equilibrium relation or the equilibrium data. Anyway, so what I did here was first to I defined the 3 components, and by the way, there is a component that's called air, and this is something that we didn't mention before because air is being used a lot, so it's defined as a separate component. You'll find that the information of the air are the information of the mixture of the gases that we know as air. So for instance here, the average molecular weight is 28.9, which is the real average, or the molecular weight of air is the average molecular weight of oxygen and nitrogen in the ratio of 21 to 79%. And so this is something that saves us time. Instead of defining oxygen and nitrogen, we define them as one component. And here there's something I want to highlight or mention, because we will need to like mention that later, that the boiling point of water is 100 Celsius, and the ammonia is negative 33 Celsius, and air is negative 194 Celsius. So there is a very wide or big difference in the boiling points of the 3 components, and this is something that we need to keep in mind while working with absorption. And for the specifications, I used the NRTL because we are using polar components. The ammonia and water are polar components, and we're not using high pressure conditions, so we will use an RTL method. So there is nothing else we need to do here. I'm gonna go to the simulation environment, and I have already defined the solvent, which is the water. It's 100% water, 1000 kilomole per hour. I put 11 bars because I'm gonna do sensitivity analysis on the pressure later. So if we have the feed pressure less than the column pressure, this is gonna make errors or warnings. So I don't want to make any warnings, and this is not going to affect the pressure inside the column because we are going to define it later. So there is no problem of having the feed or the stream pressure higher than the operating pressure. The feed gas, I have defined the flow rate to be 1000 kmol per hour, again the same temperature and pressure, and the mixture is 90% air and 10% ammonia. So this is all for the feed components. Now let's define the column, and as we mentioned before, the absorber does not or is not equipped with reboiler or condenser. The stripper can have both, or can have like open steam, as we mentioned before. So in this case, we will not use a solvent. We will use, reboiler. We're going to use a condenser. But the point here is that I don't need to have any reboiler or condenser in case of using absorber. The block or the module that we're going to use is the rat rack. As we mentioned before, the rat rack is kind of flexible column. You can use it to model different things, and it says here models absorbers, strippers, etc. So there are different different shapes of the columns here. There is a column with absorber and reboiler. There is another shape. So there are different shapes. The one that we will use is this, because it doesn't have absorber and reboiler, and it says absorber 1. So it seems that this is the right thing. We will see later that the shape does not affect, in most of the cases, does not affect the function, because it depends on the inputs, which are going to be the same for all of them. The way that you input the data is the same. But it's better to use a shape that represents the unit that we're using, especially if we are building a big flow sheet, and in this case we need to make sure that we don't get confused between the different blocks. So I'm gonna call it absorber. I'm gonna connect the feed streams and the product streams, and let's see what we're gonna do inside. So first, we're gonna go for equilibrium calculations. I have 6 stages for now. The condenser, you have the option of partial, total, and none. So we do not have any condenser, and the same for reboiler. We have no reboiler, and in case of having no condensers and reboilers, you don't need to do any more inputs regarding the specifications. There is no boil-up ratio, there is no reflux ratio, so you don't need to worry about these specs. The valid phases are vapor and liquid, and here this is a very important point. I mentioned before that the boiling difference between the boiling points is very wide, and in this case the standard convergence is not gonna be suitable. It's gonna give very bad results and non-realistic results. So the best option is to go for the wide boiling components. And this says petrochemicals, but it works for other even non-petrochemical components. But it involves wide boiling mixtures, and this is our case. And this is extremely important. It's like when we did the azeotropic or the extractive distillation. We mentioned that we have an azeotropic mixture. We here have a wide boiling mixture. So it's important to keep that in mind, and please do not forget this. It's very important. Regarding the streams, I'm gonna give or put the solvent as the fresh solvent to be above stage number 1. And for the feed gas, it says here that you need to choose a number between 1 and 7, because maybe it considers the 7 is the output as the stage, but I'm gonna make it as 6 and put this as on stage. So it's on stage number 6. I just want to make sure that, yeah, I put 6 stages. And here comes the point where I define the pressure. So I'm gonna go first for 1 atmosphere and put 0.5 bars as the total column pressure drop. So all the inputs that I need to define are now defined, and now I can run the simulation. Now I have the results. So the first thing that I need to take a look at is which is the split fraction, and here before the split fraction, here you'd see that the temperature is not high. It's 33 in the bottom and 39 in the top. It says here reflux ratio, but there is no reflux ratio. Actually, it's the rate of reflux, which is almost the feed rate. It's kind of considering this as a reflux ratio. Anyways, so for the split fraction, you'd see that the air is almost 99.9% of the air is coming out of the top product with the clean gas. Ammonia, 25 or 24% of ammonia is coming with the clean gas. So I'm removing or achieving 76% removal of ammonia. So it's achieving what I'm doing or what I'm looking for, not with the same number, but it's going in the same direction. For the water, I lost almost 7% of the water in the with the clean gas, with the gas stream coming up. So we can do the same, like confirm it with checking the stream results and seeing the mole flows. These are the numbers, the 24, the 68. So it's exactly what I mentioned. So now I'm happy that I have already used the column or used the input or the inputs in the right way so that it can work as an absorber, but it seems that the operating conditions are not the proper conditions that will achieve this. And it seems that I need to change something to achieve what I want to achieve, which is the 5% or the 5 kilomoles per hour in the top product or in the gas stream. So we have two options: either to go for the specifications and do one more specification here by changing whatever parameter that I want to change, uh, or you can use the sensitivity analysis. And I personally like to check the sensitivity analysis because it's gonna give us an option to see the effect of the parameters that we're gonna change on the outputs of the column. But before we do that, I just want to quickly do one thing, which is checking what are the parameters that we can change. Mainly, we need to change one of two parameters. The first is the liquid flow rate, the solvent flow rate, uh, and the second is the operating conditions. Back to the Excel file, you either change the operating line by changing the liquid flow rate, so you'll make the line like this, and this will improve the or increase the driving force so you can achieve better absorption. Or you can change this equilibrium curve. In case of Excel, we did not have the option to change the equilibrium curve, but here we can change the equilibrium curve by changing the operating conditions. So what I'm gonna do first is to change the solvent flow rate and make it 1200 instead of 1000, and see how this will affect the product. But I just want to keep the stream results here so we can see if there is a change. This something I like to do is to have the numbers here, and this is the row, and these are the two numbers that I'm more interested in. So I'm gonna run the simulation and see this is 18 instead of 24. So I'm improving the separation or the purification of air by increasing the solvent flow rate, but still it's not doing what I want to do. So maybe I need to go for let's say 2000. I'm just increasing it too much so that I can see what is the maximum I can achieve. So it's doing what I want to do, but I'm using um a lot of solvent. I'm losing a lot of solvent, and this might not be the most economic way to do this. Usually we increase the pressure because this is how the operating conditions of an absorption column work. This is how we do this. Um, so I'm gonna go back to 1000, and I'm go to sensitivity analysis and create a new one, and see if we create a new variable, which is the block variable. This block is absorber, and this absorber, this is the pressure. You'd see there is a list of different things. The one that you can or need to use is stage pressure. This is pressure of stage entered. You'll define which stage that you want to define the pressure of. So I'm gonna go for stage number 1, and I'm gonna go from 1 up to 10 with the increment of 1. So I'm gonna have 10 points, and I want to track the ammonia flow rate in gas, and this is gonna be stream mole flow of clean gas, and the component is ammonia. And now tabulate and run the simulation, and now it's going without any errors. If you go for higher pressures than the feed pressure, the feed stream pressures, it's gonna give you a warning. So just keep in mind that this is possible. So it seems that the pressure has a very good impact on the output. You see here at 1 atmosphere, there is 24 kilomoles per hour. It decreased to 19 by increasing the pressure by 1 atmosphere, then to almost 14. And I'm interested in 5, so 5 can be achieved in 5.25. So if I go for 6 atmospheres, it's gonna be more than enough. So I'm gonna open the rad frac and or the absorber and make this 6 bars instead of 1 bar, and run the simulation and see what are the stream results that we are getting out of the column after increasing the pressure. Now the mole flows. I am achieving 97, almost 97% removal of ammonia, which is more than what I want, which is great. And I'm losing only 14 kilomoles per hour. So it seems that increasing the pressure reduces the evaporation of water, and this is expected because it makes the evaporation more difficult. So it seems that I'm done with what I want to do now. You can do sensitivity analysis on the solvent flow rate. It's gonna be good. You can see the effect of the solvent flow rate on the removal of ammonia from air. You'd see this is something that it might be interesting. Again, this is something good to see the effect of pressure on absorption efficiency. And please do not forget the wide boiling option for the convergence. It's very, very critical and important, something that people forget a lot when they work with absorbers. So I hope it helps, and I'll see you in the next video, inshallah. Goodbye.